Okay, so we're going to talk about bisectors of triangles, okay? And you should have already covered perpendicular bisector, but just in case.
I haven't been in this class in like 2 years.
Okay.
Yeah, me either.
That's fine, that's why I'm gonna kind of go over it a little bit. Okay, perpendicular bisector is a segment or line.
You right, you put this down.
Yep. Okay, so perpendicular bisector, it's a segment or a line, and it bisects another segment at a 90-degree angle. And okay, to bisect means to cut in half. So 2 equal parts. So if I just have some line segment, oh, that's black. Some line segment. And this side is the same length as this side. And that's a 90-degree angle. Then this is a perpendicular bisector. Okay, so we have the perpendicular bisector theorem. Okay, and what this states is that if you have a point You don't hear the buzz?
Well, I mean, in general. Oh, okay, yeah.
It's sending a signal. Okay, so what it says is that if you have a point that is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of that segment. And so what that looks like have segment, right? And it has endpoints. A and B. And I take a perpendicular bisector. Okay. Sorry. And I take some point on that bisector. I'll call that point C. And this distance on it. And this distance, they're equal. So this distance is the same as that distance. basically what it does is it creates an isosceles triangle. And since this is a perpendicular bisector, we know that these two lengths were already the same. Right. Okay, anytime you see the word converse in a theory, it just means the same theory we just did, only backwards. So what this theory states is that if you have a point that's equidistant, from those endpoints, that makes it on a perpendicular bisector. Okay, so what we had before was if you have a perpendicular bisector and you put a point on it, then it's equidistance from the endpoints. Now we're going backwards. We say if you have endpoints and there's a point that's equidistant from them, then it's on a bisector.
Equidistance means equidistant?
Yes. Yeah, so equidistant is the same distance to both. So what we do is we have some line segment. Okay. And that line segment has endpoints. And if I take a point, say right there, and this point happens to be the same distance to there and to here, so this distance is the same as that distance, that means that this point is on, that's pretty, is on a perpendicular bisector.
How is it any different from?
It's not really. It's backwards.
How do we tell the difference between the two?
You don't really have to. It's just saying that you can use it both ways. It's sort of, it's an if and only if sort of a situation.
Like the
So
problem
you
only
can go,
gives you the two things.
it gives you the two
Yeah.
sides. So if I have a segment and it has a bisector and the bisector has a point on it, then it gives me two equidistant
So it's just it's
sides.
just two different, it's
Yeah.
just two options to get to the same place.
Yes, or if I have a segment and I have a point that's equidistant away, then it gives me a bisector. So I can go back, I can use it backwards or forwards. And that's what, whenever you get converse, that word converse, that's what it means. You can use it either direction and it's still true.
So it just depends on what you're looking for.
Yeah, well, it depends on what you have already. Like if I tell you that C is equidistant from A and B, then if this point here was like E, then you could tell me EC was a bisector. Then you would be able to tell me that. Or if I tell you that EC is a bisector, well then you could tell me that AC and CB are equal length. So it just depends on how you need to use it. But it's just a matter of being able to go both ways. Does that make sense? It looks the same. But what happens now is now that I know that's a bisector, that tells me that these two are equal. Okay, so here's an example.
let's say.
Okay. And I say find a B. Like 4.1. Okay, and I know that this is 4.1 because these two being the same means that these two are the same. Because it's perpendicular and these are the same. Yeah, right, since these two are the same, I know these two are the same.
What is that? Down by the 3.
Oh, that's a Z.
No, the other one.
That's a perpendicular.
No. Okay.
That's a Y.
Oh, okay.
It cut off. Sorry. Y. Okay, but this, so far, it's okay? I'm not used to having to go back and forth, sorry. All right.
That's an R at the tip, right?
Yes.
Okay.
Okay, so since these two are the same, and this is perpendicular, I know that these two things are the same length, right? So to find x, I'm going to set the two sides equal to each other. So I have 2x plus 3 is equal to 4x minus 7. So I have 3 is equal to 2x minus 7. Add 7 to both sides.
Yep.
So 10 is 2x's, so x equals 5. I could go further. I could ask you to tell me what is the length of QR. I found x, so now I could easily find QR. QR is 2x plus 3.
That's 13.
Yeah, so 2 times 5 plus 3.
Means TR is also 13.
Exactly. Which, if you check it, 4 times 5 minus 7, 13. All right. So, like I said, each side has a bisector, and the point where they meet is called the circumcenter. Now, it's not always in the center of the triangle. And that's where it kind of gets a little tricky. Okay. It's inside the triangle, but not necessarily in the center of a triangle if your triangle is acute. And if you remember, acute means all the angles are less than 90. If you have an obtuse triangle, perpendicular bisector, perpendicular bisector. I didn't draw that very well. If you have an obtuse triangle, your circumcenter ends up being outside the triangle. And then if you have a right triangle, your circumcenter ends up being on the hypotenuse.
So it's never in the center, really?
Not usually. Sometimes the circumcenter is the actual center of the triangle, but even in this triangle, that's not necessarily the center.
It's not dead center, I mean, it's
Yeah,
close to the center,
but it's not dead
exact.
center, yeah.
Um,
Now, if you have an equilateral triangle, you end up dead center. But otherwise, you're just like if it's acute, you're somewhere inside of it. If it's obtuse, you're somewhere outside of it. And if it's right, you're on the hypotenuse. But circumcenter is kind of a misleading term because that makes people go, oh, then it should be in the center. But it's not.
I just thought
Hmm.
obtuse starts with O, outside. Acute starts with A, it's around the middle. Right is right in the center of the hypotenuse.
That's really good. Did you guys catch that? The perpendicular bisectors of that triangle intersect at the point called the circumcenter, that's P, and that it's equidistant from the vertices. So what that means is PB is equal to PA is equal to PC. So if I create lines, from C to P, from B to P, and from A to P. These three lines are going to be the same length.
Oh God, so many colors.
Okay. Now, these lines here, like the DP, E, P, and FP, the bisector lines, they're not the same length necessarily. They might be if we're talking about an equilateral triangle, but in any other triangle,
What is it?
they're not the same length.
What does
It's
that say from the?
vertices, so the corners. So the lines going from the corners to the circumcenter are the same length. Oops. So you're designing a kitchen, right? You have your sink, your stove, your fridge. Obviously, there's counters or whatever around here. Sorry, I'm not going to draw the pretty kitchen. But what we would do is, if someone wanted, and they're like architects, when they design these things, or interior designers, when they design these things, there are kind of rules for aesthetically pleasing as well as functional. And if you want to put a kitchen island into your kitchen, put an island, and you want it to be equidistant, okay, You want that island to be equidistant from all those three things because those are the three things in your kitchen you use the most, right? You use the sink, you use the fridge, you use the stove. So what they do is they'll take and find the circumcenter because the circumcenter is going to be the equal distance from each of these. So we find the perpendicular bisector of this side. So that was like about 90, right? We find the perpendicular bisector of this side. And then we find the perpendicular bisector of this side.
Oh, it's not, that's tight.
And you'll put your kitchen island right here. Because this spot right here will be the most convenient spot because it's going to be equally distant from the sink, the stove, and the fridge. So that makes it easy to work with.
What spot did you pick,
You pick your circumcenter. This dot right
That's the
here.
spot?
Yeah, that's the spot. So if you're building your island, you're going to put it like right here. And that, I mean, and that's really how architects and interior tells us that if a point is on a bisector of an angle, then it is equidistant from the sides of the angle. So if we take some angle and we bisect it. Okay.
What angle are you using?
I'm just using any angle. So if I, no, I just call this like A, B, C. Just
Wait.
random angle.
You said that if we go online, we could print out all of it,
Yeah.
right?
Are we allowed to use the notes on our test?
Sometimes. So,
I got one big fat question.
yes,
Are these gonna be able to cut it too as notes?
notes are for you. not for me.
Because that's what happened, first semester in geometry.
This angle ABC, and we bisect it with, you know, BD. That means that this angle is now cut in half.
Slow down, what'd you say?
So this line, this green line, BD, is the angle bisector. So it cuts the white angle, ABC, in half.
Half, yeah.
Yeah. So these two now are equal angle measure, right? Well, if that happens, then what also happens is that if I then measure the distances here and here,
No, you said, what'd you do?
if I have a point, just any old point, right? If I have this point, F, we'll just call it F, it could be any letter, is on the angle bisector, then it is equally distant from the two sides.
So no matter where you're at on the line.
So if I come back up here
Alright,
and
you
I
said
do
F, you said F is what?
equally distant from the two sides. So any point on this bisector is going to be equally distant from the two sides of the angle. So if I come to G, then these two sides, these two distances will be the same. So I can take any point on that bisector and it'll be the same distance away from the two sides of the angles. Does that make sense? And if you think about it, it kind of makes sense anyway because the bisector cuts the angle in half. So if that whole width of the angle is cut in half, it kind of makes sense that it would be the same distance away from both sides, right? Logic?
I get what.
And if I go inside this angle and I pick some point right here, D. And I was very careful and I measured, and when I was picking out D, I determined that this length here was the same as this length here.
I can't read the last line.
This one?
It says
The
then.
red is
Okay, then it is on the bisector of the angle. Red doesn't work well? All right. Let's do green. So I go and I got an angle and I pick a point and I'm careful and like I said, I measure. Actually, I'm gonna lower that. And I measure and I make sure that these two distances are the same. Then what that tells me is if I pick a point in the center and it's the same distance from each side of the angle, then the bisector goes through that point. So then I can come out here. The bisector. And if I draw a line or a ray through there, it becomes the bisector. So the bisector theorem, angle bisector theorem, tells me if I have a bisector and I pick a point on it, then it's the same distance from each side. The converse, so going backwards, is if I have an angle and I find a point in the middle that's the same distance, then I can draw a bisector through it. Does that make sense? So it's again one of those, you can go both ways to determine what you need kind of situations. So what you have is a triangle. Any old random triangle. And when I take the angle bisectors from each of these angles, that's not going to work, is it? Okay, so I take the angle bisectors from each side. Okay. That gives me the point, the incenter. Now this one is sort of going to remind you of Circumcenter, but it's not. Remember how on the Circumcenter these lengths were all the same? But the lengths to the side were not? But remember those were the perpendicular side bisectors that made the Circumcenter. The angle bisectors make the incenter, and then the incenter is equidistant from the sides.
So the actual lines that this stuff aren't equal.
The lines that make it are not equal. Like the yellow,
Yes.
not equal. But the green are.
But the product is not connected, makes it equal.
It's because of that angle bisector theorem. Does that make sense? So this
that-
angle
So that-
bisector?
Does that meet dead center?
No, only in an equilateral triangle.
So why are the lines the same? Why are the green lines?
Because we just talked about the angle bisector, right? So this is one angle. This is a bisection. This point is equally distant from the two sides of the angle. But then we have this other angle with this bisector, which makes these two lengths equal. And then we have another angle with another bisector that makes these two lengths equal.
Okay, so you just have, it's just 3 bisectors that meet.
That make a point that are equally distant from the sides.
That's where I got confused, is where were all these lines coming from and why were they?
Yeah, the yellow are the bisectors, so yellow.
Triangle, as in 3 angles and 3 different bisectors.
Yeah.
But they're all equal same.
No, the yellow aren't equal. So the yellow are the angle bisectors. The green are the distance to the side. And they are equal.
Every corner has a different bisector.
So if this is, so that's ABC, so we'll call this D, E, F.
Was there you two
Yes. Hold on one second. So PD is equal to PE is equal to PF. I am, office hours are Monday.